So now we're going to look at how a pipeline, a simple pipeline like the one in the previous example, can be implemented in a real architecture. Here's an example, a schematic of a 5-stage pipeline, fairly similar to the one we described before. Let's first identify some of the important parts of this pipeline. We have a register in the far left that contains the program counter, the PC, pointed to the next instruction to be executed. As you can see, it points straight into the instruction memory. So even though in this schematics, the instruction memory is just a single box, and we assume that we can get data out of that in just one cycle, we all know from early in the course that what's hiding inside this box could actually be a fairly complicated structure with an instruction cache, ITLB, lots of scary stuff, level 2 cache, level 3 cache, all the way out to memory. But now when we discuss the pipeline, let's assume best case and that we can get data out of instructions out of that box in one cycle. Further to the right, we have the register file. So this is where we keep the 32 or whatever number of registers has been defined for this architecture. Even further to the right, we have the ALU. This is our hero that's going to perform the useful work, perform the executions. And then even further to the right, we have a box called data memory. And likewise, instruction memory, we know that what's hiding inside of this box is the entire hierarchy, including cache coherence and NUMA effects and so on. But for simplicity, when we discuss pipeline, let's for now assume that this is a box where we quickly can get the data that we're interested in. Up in the top left corner is another ALU, and this ALU is connected to the PC, and this ALU is an ALU that has a specialized job to always add 4 to the program counter. So that assumes here that we have an instruction of 4 bytes. So every time we execute an instruction, we need to increment the value of the program counter. So these are our main characters of this movie. Let's see how they work together. So as I said, this pipeline is divided in 5 different pipeline stages, symbolized by the boxes below, but you also have the names written above what these boxes stand for. So we have the stage to the left of this bar here called instruction fetch pipeline stage. We have the instruction decode register fetch pipeline stage. We have the execute address calculation phase. We have the memory access phase and the write back phase. And of course down here you have the shorter names for the different phases. So this is a 5-stage pipeline. The one we discussed before was a 4-stage pipeline. The difference here is that the 2 last pipeline stages here was combined into a single pipeline stage in the previous example. So here we have access to memory as well as write backs, not write backs in the context we discussed before, but write backs to the register file. So let's see how these pipeline stages and the main character of this movie work together. So what's happening here in the first stage of this pipeline, the instruction fetch stage, is that we will get a value out of the program counter, and that value is the address pointed to the next instruction to be executed. We're going to read out that instruction, those 32 bits representing the next instruction to be executed, and put it in a latch. So this vertical bar here symbolizes a latch in the pipeline design. So that value is going to rest here safely in this latch at the end of this clock cycle. As you can also see, the +4 value that we added here is going to be looped back all the way through here, and the value PC +4 is going to be put in the program counter. That's the most normal case of the execution. And as you also can see, there is a latch here, so we're going to remember the new value at the end of that first instruction. So now we have the 32 bits representing the instruction sitting in this latch over here. So the very next cycle, those bits can be read out, and part of this representation of the instruction are bits representing which register to read, which register to write. So here we have the destination register, the source register, and the source register, so 3 register values that we will use to access the register file here to get the right selected registers out of this file. So we more specifically are mostly interested in the 2 source registers here, and we will put the values coming out of those 2 selected source registers into this latch A and latch B on the outside. From the representation of the instruction, we can also get the intermediate, those 16 bits of constant that some of the instructions contain, and we can store that as well in the latch over here, the immediate latch. So we take those 16 bits and we have to sign extend them, and we have to make them look like a full-fledged 32-bit value before we latch them here, because we want this value to come out here to look just like the values that came out of the 2 registers, and they are sign extended 32-bit values stored in each one of those registers. So here we have 3 sign extended 32-bit values. That's the end of that phase, and then comes another clock tick, and now all the values stored here will be available. Actually, I forgot to mention a value, important value stored up here. This is the next program counter value. It's also being latched at this point in time up in this register over here. So we have the next program counter, we have A, we have B, the 2 source registers, and we have the immediate. Now, the job of the next stage, the execute stage, is to put this ALU into business. So here we have lots of different ways of putting the ALU into business. We have 2 muxes here. The mux this top mux can either choose to read in the PC value that comes from this latch over here, or one of the source register values, and put that as one of the inputs to the ALU. The lower mux can choose to either put the second source register value into the ALU, or put this intermediate constant into this ALU. And exactly the choice these 2 muxes will make really depends on what instruction we're executing. So these bits here that we stored at this point in time, even though it's not shown in this picture, some of those bits also travel with the instruction, and at this point in time a special magic of those bits will be used to choose this mux, saying if this is a branch we're going to try to calculate the next address for, we need the PC value here, otherwise we can't make that calculation. If this is the type of instruction that has an immediate in it instead of 2 source register values, then this mux here will get a special signal that is carried all the way from over here that will control it to take the lower input of the 2 and input the immediate. Otherwise, it will input the value we got out from the other source register and put that into the ALU. So that is to make sure we get the right data to the ALU. If this is a branch that's executed at the very same time, we may want to know if the value from one of these registers is equal to 0. So that's what we'll take the value up here, and this 0 0 question mark will produce a single bit that will be stored over here in this output latch, conditional output latch. So now the ALU can perform its work. It could be adding 2 register values together, could be calculating the next address we need to access from memory, or it could be calculating the next program counter that we need to make the execution from. That value that is produced by the ALU is put into this ALU output latch here. At the same time, when we perform store operations, we also need to store the value from one of the registers, the value that we're going to write into the data memory in the latch here, so it's ready to go. Now, during the next stage, the memory access stage, if we, for example, do a load operation, that means that this ALU output will now contain the address of the data that we'd like to load the value from. So we're going to put this value out here. This is going to be the address into the memory, and if that's a load operation, we're going to store the value in that memory location at the end of the next cycle in this latch over here, load memory latch. Or if this is a store operation, then the ALU will also now contain the address of the memory location we'd like to store the data to, but instead of reading the data out, we're going to take the store data from here that was latched here and write that into that memory location. If it was just a normal register to register with operation with two register values or a register immediate value producing some kind of result, that result will simply go along this path here and will be latched at this point. And if this the output was the next address from which we should fetch the next instruction, so this is a conditional branch instruction, that value is now sent to this max here, and depending on these condition bits, we can choose to either take the purple input or the gray input when we would like to fetch to update the PC pointing to the next instruction to be executed. Finally, we have the write-back phase. In the write-back phase, you either take the ALU value you stored here, or for a normal ALU operation, or if it was a load operation, you take the value that comes from this load latch, and which one you choose depends on this max, and that max is controlled by exactly which instruction, type of instruction we were executing at the very beginning here. And depending on that, we're going to send the data back to the register file and update the very destination register. So we have to remember what destination register we saw 3 cycles ago. So we would make sure that whatever was identified over here, that register is the one that's going to get updated with this brown data. We have what's called an early register right here in this design, which assumes that the data that's being produced in this very cycle and written into the register file can be read out of this register file the very same cycle. So if we're reading the same register as we are writing in this cycle, we're actually going to get the new and exciting value read out at this stage. So there are some fundamental limits that will force a pipeline like this to stall. Typically, in the ideal world, we always want this pipeline to advance each instruction one pipeline stage per cycle, but sometimes we can't do that. And there are some fundamental reasons for this, and we give them unique names. So these are names sort of similar to Mark Hill's why do you miss in the cache kind of names that we're going to discuss quite a lot in this course. So one could be what's called a structural hazard. It means that you would like to advance data to the next pipeline stage, but there are 2 instructions that sort of claims the same kind of hardware resource. The easiest way to explain what may be going on here is that assume that we had a unified instruction and data cache. Okay, so it's only a single cache, and we read both instructions and data out of this first level cache. And assume that we would like to load a word from this cache, and also we would like to do an instruction fetch from the cache in the very same cycle. That's an example of a structural hazard, where we have 2 simultaneous activities that wants to come to use the same hardware resource. So that's bad for a pipeline design. Data hazard is probably more common than structural hazard in our pipeline design. So data hazard is depicted here by a simple example. Let's say that you load some value from some memory location into a specific register. And of course, as we know, this is going to be loaded from a cache. If we are lucky, we get a hit in the cache, and this may take 2 cycles, 1 cycle or 2 cycles, depending on how fast the design is. But it may also take 150 cycles or 200 cycles and 250 cycles if we have a NUMA kind of memory system. So this could take a long time. And unfortunately, the very next cycle depends on that this data is available in R1, because here we like to add R1 and R7 together and put the result in R5. So what we have detected here is a data hazard. And this is also bad for pipelines. And the third hazard is what's called control hazard, which we already have discussed, and that is the fact that in a pipeline design, when you execute a branch, it's going to take many cycles until you know whether or not this branch will be taken. So it's a hazard in that you cannot safely just go on and execute the next instruction unless you really know what you're doing here. So typically, this is another reason why you of this kind of hazard. So structural hazard, data hazard, and control hazard. So one way to solving problems relating to hazards is that you serialize and you stall the pipeline whenever hazard happens. So after this branch, you may stall the pipeline, which means you will not start any new instructions right after this branch until you know it's a safe distance, and you know that the branch will have a chance to have an opinion whether it will be taken or not, and also you have a chance of calculating where to fetch the next instruction from, and then and only then will you let a new instruction into the pipeline. Likewise, if you have a data hazard, you will not continue and execute the next instruction until you safely know that the previous instruction that you're dependent upon has produced the data value. And likewise, for structural hazards, of course, you have to stall either loading of the instruction or loading the data value. You can't do both at the same time. So we have to stall the pipeline, or what we often refer to as to introduce bubbles in the pipeline. Talking about data hazards, there are also three different kinds of data hazards that we will talk about. So considering a code sequence where we first have an instruction I operating on some kind of memory location or some data somehow, some register or some data. And then we have some following instruction I plus 1 operating on the same piece of data, same memory location, or the same register. Then we say that we have a read after write hazard if the previous instruction, the first instruction, is a write instruction that updates this value, and the following instruction, this instruction, is a read instruction. So that was the example of data hazards we saw in the previous example, where we did a load into register, and that register was read in the very next cycle. So that's called the read after write hazard. But we also have write after read hazards, where this is a read instruction and that's a write instruction. There is also dependence between these instructions, and the dependence is that we really have to make sure that the register is read before we let the following instruction update that register. This doesn't make sense in the pipeline I just showed you, because in that pipeline things happen sequentially in a nice order. But later on, when we talk about out-of-order pipelines, this will make a lot of sense. Another kind of hazard that will make sense when we talk about out-of-order pipelines, it's what's called write after write hazard. So if the first one is the write instructions, we change the register, this register A, and the second instruction is also a write, so we change the value of register A. Of course, we also have to make sure that these writes are performed in the right order, because the following instruction here, of course, has to see the value of the second write. But if we perform these two writes in the wrong order, that means that it would see the value of the first write. So it's called write after write hazard. One example where this kind of data hazards, and specifically read after write hazards, was in the example of the simple pipeline. So the problem with that, one of the problems with that simple pipeline example was that it wouldn't work. I was lying to you. We had a data hazard in that example. So here we assumed, at least I assumed, that this was the programmer's intention, that the green instruction that loads a value into register A that the programmer wanted that newly loaded value of A to be incremented by 1 and then put in register B. But there is a dependence here. So even if we assume that this load is a cache hit and that data is returned right away from the memory, you can see that the problem arises right here at the stage where the gray instruction is in the register read and the green instruction is in the execute pipeline stages. Because right here, at this point in time, we are calculating the address from which we're going to load the value into register A. But at the same time, we are reading the value of register A. So the gray instruction is reading this register value here. So what's happening here is that the gray instruction is going to read the old and boring value of register A, not the new and exciting value that this load instruction will put into that register. So clearly, this was not what the programmer had in mind. And actually, we have another dependence here as well. That's going to be potentially also could create problem for us. Of course, this conditional branch at the top here wanted to see compare with the newly updated value in register C, but since it is executed the very next cycle, for the very same reason that the gray instruction would get an old value, the brown instruction would also get an old value. And we're going to talk about different ways of solving these kind of problems in a little while. So the problems can be solved by what's called static techniques, and this is techniques that the compiler tricks. So the compiler can reorder instructions and make some of these problems go away. All of the data hazards could potentially be made go away by a good compiler. Or it could be it's solved by dynamic techniques. And when we say dynamic techniques, we often refer to hardware mechanism, something that, every time an instruction is executed, we're going to detect that something is wrong and we're going to fix it. That's the dynamic part of it. Static, that assumes that the compiler, is going to solve this problem once and for all when the high-level language is compiled into machine code, and the problem will never occur. So there's a static solution, dynamic solution. And then we have hybrids of both, and we will see hybrid technique in a couple of videos when we start to talk about what's called very long instruction word computers.